Hello everyone, my name is Rayani Keri and I'm presenting my project on financial forecasting. I'm predicting the delta value of a stock, which basically measures the change in stock prices. I'm following the CRISP DM methodology. So this is the process I've been following: business understanding, data preparation, data modeling, evaluation and deployment. So predicting the change obviously yields significant profit to the companies. So which is why I've chosen this project. Coming to the data understanding part. The data I've collected is from G Research, which comes under the company called Trenchant. So they research investment ideas and also develop the research and execution problem to deploy these ideas in markets globally. So here's what my data set looks like. This is the index which just gives the rows. So there are basically four markets, and the days goes for it's the data set is for 2 years, starting from 1 to number 729. But half of the data is in the test data set since it was taken from a competition. There are about 3000 stock values, and these x0 to x6 are the predictors. Y is my target variable, and the weight is given in the data set, so which will we can calculate the weighted mean squared error from this. So two of my features had missing values and I have imputed them using the mean. You can see here. And I created a mode function to calculate which of the stock is occurring the most. And I took that stock to continue with my data further. Here's what my final data set would look like. X0 to Y and weight. It has 249 observations with 16 variables. So coming to the data exploration part, so I did the histograms, line chart and skewness. As you can see here, most of my features are positively skewed. X0, you can check the others too. Like most of these are going towards positive skew, and since the data is very, due to fine security purposes, the data was encrypted. So the data set which I have is something similar to this. This would give a better understanding of what the data set is. This close, high, low, open are the stock prices for that particular day. And these things like X, 3A, 3B, 3C, 3D are like the high, open, close stock prices for my data. So I'll be using log transformation to convert this positive skewing to normal distribution. So for detecting the outliers, I've used box plots for all the features. So starting with x0 and x1, this has, as you can see, the values above 0.65 outliers here. So to find the collinearity, I use the cogram function from the cogram package. And we can see that there are a lot of collinearity between the predictors, which is not good and which would be a bad fit for the model. So to overcome this collinearity problem, I'm gonna apply principal component analysis. And to overcome the outliers and the positive skewing problem, I'm gonna do a log transform, as you can see here. So doing the log transform basically converts the positive skewing to normal distribution, which also removes the outliers. Not exactly removes it, treats it. I'll show you a histogram of before applying the log and after applying the log. So I've implemented the PCA using the prcom function, and I've scaled my feature values here itself. As you can see, the histogram have been changed to normal distribution. This is x0 before applying the log transform, and this is after applying the log transform. So my PCA has about 13 features. And as you can see, the collinearity between the predictor variables have been removed. So for training the model, I've taken the first 70% into the train and the next 30% into test dataset. Coming to building models, I've built 5 models: linear regression, regression trees, a neural network, support vector machine, and Xgboost. For linear regression, I've just used the LM function from the caret package and gotten multiple R squared value of 0.518. And the residual standard error for this was also 0.000036. Coming to the regression trees, I've used the rpart function from the rpart package. So this is what my tree looks like. For neural network, I've used the neural net package with a hidden parameter 1. For support vector machine, I actually tried different kernels like vanilla dot, but then rbf dot gave me better results. And for Xgboost, I've used the Xgboost package. The thing here is Xgboost only supports the matrix format, so I had to convert the test and tree into the matrix format. And the end rounds here, basically in each round the RMSE keeps improving. For now, I've given the end rounds as 20. So coming to the evaluation part, I've evaluated the model based on the correlation between the predicted and the true value, mean absolute error, root mean squared error, and weighted mean squared error. So I created 3 functions: MAE, RMSE, and WMSE to calculate these metrics. Applying it on the linear regression, I got a correlation between predicted and true value as 0.60 and RMSE of 0.00000439. And with regression tree, this variable importance gives us the importance of each single features, like the PC3 being the strong predictor and PC7 being the least significant predictor. I got a correlation of 0.56, which was slightly lower than the linear regression model, and also the RMS is slightly higher than the linear regression model here. But the neural network did not really fit well, and even the correlation was bad, as well as the RMSE was increased really high. The support vector machine which I used from the kernel app package gave me a correlation of 0.64, and RMSE was lower than that of linear regression model, which is 0.000362. Yeah, coming to the Xgboost, I got a correlation of 0.953 and RMSE of 0.00040, which is the least. So this is the best model as of now. So for evaluation with K-fold, I use 5-fold cross validation for LM model with DAG package, and for neural net I've used it from the caret package, which I got similar results as that of the previous neural net model. Even for the support vector machine, I used the caret package for 5-fold cross validation, and I almost got the similar values, as you can see. In fact, the mean absolute error increased from 285 to 335, and also RMSE also increased, and the correlation decreased by a little. So for tuning the models, I tried the stepwise backward elimination, which gave me the similar results. And for tuning the regression trees, I use the CP parameter to change the values, but then here also I got the similar results to that of the previous model. But in Xgboost, I added a new parameter called early stopping rounds, where it stops the rounds if the loss does not change for 5 consecutive rounds, and I increased the number of rounds to 40. So this increased, as you can see, the train RMSE is 0.00019, which was 40 earlier, and the correlation also increased to 0.957, and it's having the least RMSE as of now. The ensemble I've created here is from the Carrot ensemble package, and I've used linear model, RPart, SVM linear, and neural net. But it gave me pretty much the same results here. As you can see, I've got the correlation of 0.60, 0.41, 0.58, and 1.1, LM being the best. So for comparing the models, I created a I created a matrix where I've added all these values. So XGBoost tuned, as you can see, has the best correlation, which one being the perfect model, and RMSE should be least for a model, and XGBoost has the least RMSE here. For better understanding, I've also plotted it using the Plotly package, which is available in R. The XGBoost has the 19.19 mu of RMSE, which is the least. And here for comparison by correlation, here XGBoost has the maximum correlation 0.957, and this being 953. So even when we're comparing by mean absolute error and root mean squared error, which should be the least for a model, XGBoost has the least of both. And this is the stock measure which I have predicted. As you can see, for day 279, the value was 106.439 mu. So to conclude, I would say that the XGBoost performed really well, and it gave me the least RMSE and WMSE, and also it had the highest correlation. Thank you guys.